Kia ora koutou. This is the first video from this year's school exam for Level 3 Calculus. I'm starting with one of the excellence questions in the differentiation paper. And it's a pretty classic setup where we've got a sphere with a cone sitting inside it. And we're given a really nice hint that made the problem much easier. What I'm going to do in this video, though, is go through 3 different ways that are going to get us to the end of the problem. The first 2 are pretty similar and they're quite efficient. The third one is a really, really slow and very easy to muck up way that a lot of people in my class tried to use. Now, just before I start, I just need to warn everyone that my dog is currently mucking around in the kitchen, so there could be a couple of dog interruptions in here. All right, well, I think I have got rid of the dog, so now we're good to start. Let's just read through the question carefully and look at the hint that we're given. We've got a sphere of 9 centimetre radius, and it's got a cone fitting tightly inside it, and the cone has a height of h and a radius of r. So you can see we've got h here is that whole length there, and r is the radius of the cone, right? R is not the radius of the sphere because the sphere, we're not choosing anything about the sphere, right? We're given the sphere, and we can see that this length here is 9, right? And that's fixed. What we have to do is to choose r and h to get the biggest possible volume cone, right? So we're calculating the maximum volume of the cone. We don't need to show that it's a maximum, so no second derivative stuff. And then there's this very, very good hint that I think was quite nice and generous from Mr. Black. So let the height from the center of the base to the center of the sphere be h1, right? So what that means is that we know when we draw our cone out in 2 dimensions that we can draw it out like this. So we'll draw, oh, wrong pen. Okay, so in 2 dimensions we've got the top of the cone is here, the center is here. Let's plonk our cone in here like this. Okay, so this bit here is r, this whole thing is h, but this bit from the center that I'm drawing in now, this is h1. So what we need to do is to figure out that the volume of a cone is 1/3 pi r squared h. And we need to choose r and h. As usual, we need to eliminate one of those variables. So we can start by saying h1 plus 9 is equal to h, right? So this bit up here that I'm drawing in now, that's 9. That gets us to the center. And then there's this h1 here. Okay, so that's all good. And then what most people in my class saw really well is that if we use Pythagoras, we can build a relationship between this, and we know that this side here must be 9, right? I'm getting ahead of myself with the 81. So let's just write down some statements that we've got. We've got h is equal to h1 plus 9, and we've got r squared plus h1 squared is equal to 9 squared. That gives us r squared is equal to 81 minus h1 squared. Let's look at what our next choices are. Well, this is the thing that we're trying to maximize. And we've got 2 options here. We can replace h, or we can replace r squared. And a lot of people didn't stop and think about that before they did it. If we replace r squared, things are going to be really easy. If we replace h, things are going to get really, really messy fast. We also notice that here we've got h instead of h1. So we're going to get the whole thing in terms of h1. And then we'll differentiate with respect to that variable. So v is going to equal this. And we replace h with h1 plus 9. So expanding that out, we get 1/3 of pi times 81 h1 minus h1 cubed plus 729 minus 9 h1 squared. To maximize it, we're going to differentiate with respect to h1 and set it equal to 0. Now, one thing that we can usefully do, hopefully at this point in the year, is since we've just got that constant sitting there, we can do this, we can leave that sitting in here because we know that's going to be in every term. So we get 1/3 pi times 81 minus 3h1 squared minus 18h1. And that has to equal 0 for a max. So it doesn't really get much easier than this for a level 3 excellence question if you've done it using this method. What have I got now? Well, I've got this has to equal 0. Dividing through by 3 gives me 27 minus h1 squared minus 6h1 is equal to 0. h1 squared plus 6h1 minus 27 equals 0. And we get a really easy quadratic for h1. So we have h1 plus 9 or h1 minus 3. We know that h1's got to be a positive number or 0. So h1 can't be equal to negative 9. That means that h1 has to equal 3. This gives us a height for the cone of 12, so that's 3 plus 9, and an r squared of 81 minus this, 3 squared, so r squared is equal to 72. Finally, we get the volume of the cone, which is 1/3 pi r squared h, so 1/3 pi times 72 times 12. 12 over 3 is 4. That gives me an exact answer of 288 pi, or a more useful for real life answer of 904.77 cubic centimetres. Okay, so that's method 1. Now that took a wee bit of time because I was doing the setup. I'm going to show you a slightly different take on that, which is that if you didn't feel confident working with H1, we could instead go back up the top and work with H. So I'm going to leave that picture there and then erase a whole bunch of stuff underneath it, just a sec. Right, so going back to where we've found the relationship between R squared and H1 squared, we've got this. And last time we got all of this in terms of H1. This time I'm going to instead work with this and say that H is equal to H1 plus 9. So H1 is equal to H minus 9. Where does that get me? Well, I've got 1/3 pi, and then R squared is 81. Where are we? 81 minus H minus 9 squared times H. That gives us 1/3 pi 81 minus H squared plus 18H minus 81 times H. So I'm just expanding those brackets out, and that gives me 1/3 pi times 18H minus H squared times H. So 1/3 pi times 18H squared minus 1/3 pi times H cubed. I don't know why I'm putting the times sign in there. That looks terrible. Just get rid of that. So you can see this is an even cleaner differentiation. So 6 pi H squared minus pi on 3 H cubed. We haven't differentiated yet. So now at last we go dv by dh is 12 pi H minus pi H squared equals 0 for a max. And we get H, let's divide through by pi. What do I get? Brain going very slow. 12 minus H. So this way we get the full height of the cone straight away. So H equals 0, or H is equal to 12, but H can't be equal to 0 or we wouldn't have a cone at all. Now we get R squared, substituting back in earlier, is equal to 18. What was it? 18H, so 18 times 12 minus 12 squared, which gives me, of course, 72, and we get the same answer. Right, so now buckle up for the last way to do it, which, as I said, was how lots of you in my class tried to do it, and it's just so much worse. So the reason I'm going through this is that this comes up quite often with level 3 merit and excellence problems, and if we're trying to maximize something, and we have a nice easy expression for a square, it's usually going to be easier to replace that. The minute we start working with square root signs, things are going to get bad, and this is a pretty bad example of what's going to happen. So in here, we had that h was equal to 9 plus the square root of root 81 minus r squared, right? So that came from our setup at the start. If I don't look and think before I get going, this is the expression that we're going to work with. Right, you might want to pause the video and just have a go at cleaning that up and then at differentiating while I get rid of this work. So we can get there, and I'm going to go the whole way through to the end just to give you some good practice at differentiation skills. We'll start by expanding. We get 3 pi r squared plus 1/3 pi r squared, and I'm going to write this with a fractional power. Now dv by dr will give me 6 pi r, but you can see that I need to do the product rule on this, right? So it's going to be 1/3 pi r squared for this function times a half 81 minus r squared to the negative a half times negative 2r. And now I have to have my second product rule term, so we'll have 2/3 pi r times this, and that has to all equal 0 for a max. Happily, there is some cleaning up I can do in here. I know that r is not equal to 0, and I've got pi, so I can divide through by both of those things. So what we're doing is we're solving this equation, dividing through by the things we can divide through by are 6 minus r squared. Let's see. I think I need to clean up first. I'm going to clean it up first. So forget about the dividing. You can see that already, even though I've done the working for this before I made the video, it's getting pretty bad. Let's see. So we've got 6 pi r minus 2 pi, so ticking off as we go, 2 pi r cubed over 6 root 81 minus r squared plus 2 pi r over 3 equals 0. Right, now I'm going to divide through by pi and r. Whoop. That gives me 6 minus, this is a 3, r squared over 3 root 81 minus r squared plus 2 over 2 root 81 minus r squared equals 0. So this is actually good algebra practice for some of you in my class, so don't like stop watching. Just make sure that you don't use this method to solve the problem. But it's good practice at getting common denominators. It's just pretty hideous for problem solving. Right, where's my pen gone? Here we are. Common denominator. We need 3 root 81 minus r squared. That gives me 18 root 81 minus r squared plus, just timesing in this bit here, I get 2 times 81 minus r squared equals 0. Right, you can see in my earlier working I was done by now, right? The next step is we can ditch the denominator. 18 root 81 minus r squared plus 162 minus 2r squared equals 0. Cleaning this up gives me 3r squared minus 18 root 81 minus r squared minus 162 equals 0. Dividing by 3, r squared minus 6 root 81 minus r squared minus 54 equals 0. Gross. Now the best thing to do here is I'm not going to do a u substitution. I'm going to square both sides. I get r squared minus 54 is equal to 6 root 81 minus r squared. Squaring both sides gives me, oh, I'm running out of time. There we are. And from there you'll get to the